So this presentation is on finding the probability of events. That's module 9 over here in our OLI textbook. In the workbook, where I'm picking up today is topic 3 it's called modules 8 through 10. It's all one sort of chapter in the workbook. And this is topic 3 on the logic of events. So topic 2 needs to be done before you do topic 3. Topic 2 in the workbook was just introducing probability models, and that would be on pages like 98 through 102 in the workbook, in the textbook. So 98 through 102 in the OLI textbook corresponds to topic 2 in the workbook. And then topic 3 in the workbook picks up with this probability rules list on page 103 in module 9 in the OLI textbook. And what I'm going to do today in this video, I've taken the probability rules and I've broken them up into 3 separate videos. And so this one is going to talk about the law of the complement and the law of unions, and it's going to talk about mutually exclusive events. So in the textbook on page 103, we're getting some of the axioms back from topic 2, that the probability of any event is between 0 and 1. We get the probability of the whole sample space, the list of all the possible outcomes. The probability that you get one of those has to be 1 or 100%. So your list of possible outcomes should not leave out anything that could happen. And then we come to this complement rule and the union rule after that. So over here in the workbook, we have some vocabulary list, and then we mentioned the law of the complement and the law of the unions. And this video will be fairly brief. I'm just going to illustrate where those come from with some pictures. So, we have some flowers. Let's say your flowers are out in a field, and you're going to go out there blindfolded, and you're going to spin around a lot until you don't know where the flowers are, and then you're just going to kind of feel around until you get a flower. And some of those flowers are large and some of them are small. So we're going to let L be the set of all the large flowers. And then some of the flowers are red and some of the flowers are blue. We're going to let R be the set of all the red flowers. And we're going to have another event. So each of those is an event, right? So we have to talk in terms of a repeatable experiment. And so the repeatable experiment for this story is you select a flower at random. Okay, and then what is an outcome It's the flower that you get. Not the color of the flower, not the size of the flower, not the type of the flower, it's the flower. So we have an experiment. We know what sorts of outcomes are possible. The sample space. That's the set of all the possible outcomes. In other words, it's the set of all the flowers in the field. So that's these 20 flowers. Each one of these letters that I've written up here is supposed to be a flower. I'm just not a very good artist, so I wrote the letters. But the sample space is the set of all those 20 flowers. Now, sometimes on tests, I might ask you to identify the sample space, and a typical incorrect answer would be for somebody to say 20. Is there 20 flowers? But it's not the number, it's the set of flowers, the collection of them. Okay. So it's the set of all the flowers. Now, I'm going to make a probability model that would tell us the likelihood of any particular event. So an event in this story it could be any set of these flowers. So L, the set of large flowers, L is the event that we select a large flower. We identify the event with the set of outcomes. The event has happened if you get one of the outcomes belonging to the set. Okay, so okay. So L's that set of flowers. Okay. Now let's make a probability model that would let us predict the probabilities of events. And so our model could assign probabilities to all the outcomes, all the elementary events, sets containing just one outcome. The event that you get that particular flower would be one elementary event. Our probability model can assign those probabilities any way we want, as long as the probability of the entire sample space is 100%. So we had the list of axioms back in topic 2, the 4 of Kolmogorov's axioms, the requirements for making a model. And as long as you satisfy those, you're not going to contradict yourself. All the probabilities are between 0 and 1. The probability of the total, the whole sample space, is 100%. The probability that you get no outcome at all, the probability of the empty set has to be 0. And for disjoint events, the probabilities have to be additive. Well, you can do this in many different ways, assign different numbers to each flower. But I'm just, to keep things simple, I'm just going to assign an equal probability to each flower. There's 20 of them, so the probability of selecting any particular one is 1/20th. Okay, so I'm going to use equally likely outcomes. So I'm making an ELO model. And so, of course, when you make up a probability model, you don't know if it's true, and you never find out for sure. You'd have to repeat the experiment for a long time to see if your model appears to be close to the right percentages. So when I say the probability of getting this flower is 1/20th, I mean, if I do this experiment over and over again, I blindfold myself, I lose track of where I am, I pick a flower, I do it again. Many times in the future, I think 1/20th, I'm predicting that 1/20th of the time I'll get that particular flower. And so it's just a model based on my assumptions about how the world works. Okay. So we've got our model. Now I want to get around to a couple of simple things. The first one, law of the complement. So this not L, or some notation uses a tilde. I'm using this little not symbol, but not L, okay, is the event that you don't get a large flower. Or we identify events with just sets of outcomes. So another way to say this is that not L is the set of all the flowers that are not large. Okay, so what's the probability of not L? With the equally likely outcomes, we just count. We count how many outcomes there are in not L. And divide by how many outcomes there are in the sample space. So I'm going to use the letter U for the sample space. Okay. So, you can just count to get the probability. Now, I want to point out, let's do a little calculation and get another equation. The number of flowers that are not in L is the total number of flowers minus the number that are in L. So the size of not L is the size of the whole sample space minus the size of L. I just replaced the numerator there. And then I can use the distributive property. Get the size of U over the size of U. Minus the size of L over the size of U. So the probability of not L is 1 minus the probability of L. Now, so you can use this either way. Whichever one of them you can, P of L is 1 minus P of not L. So if you know one of them, you can find the other. So this is the law of the complement. So if there was a 60% probability of L, then there's a 40% probability of not L, just 1 minus. Okay. So what I want to do next is the law of unions. And we'll stick with our story about the flowers. So I want to do what's the probability? Well, first let me just talk about the sizes of these sets. So I'm making the union of the large flowers with the red flowers. So the union, it includes all the large ones and it also includes all the red ones. So that's all these. Get the red and large both included. A flower, an individual flower, is in there if it is red or large. So, you notice to count them, I could just count the large flowers. And count the red flowers. So I've taken these 10 plus these 10, and I've got 20 so far. And that's too many because these guys right here, the large red flowers, they got counted twice. So if I stop here, I've got too many. I've got to subtract away these 4 large red flowers. See, because they've been counted twice, so if I subtract them away once, then they've been counted the right amount. And so, it's like I've got the 10 across the top here. The 10 red ones. And I need to subtract those 4. So what's the symbol for that event? The event consisting of these 4 outcomes. That's the intersection of L with R. It's like 2 streets crossing. Here's the large street, and here's the red street. And their intersection is the shared part, just like the intersection of two roads. Okay. So what do we get? Oh, except there were, oh, I was wrong though here. There were only 8 red flowers. Okay. So I get 14. We could have just counted, but I want to do a little calculation, come up with another equation that we can reuse. If I divide by the size of the sample space, on both sides of the equation, use the distributive property to divide out here, divide all 3 of them. So I get the probability of the union, the probability that L or R is the probability of L plus the probability of R minus the probability of L and R. Now, that's called the law of unions. Now, because of the way it's written, you're thinking, okay, I can use this to find the probability of the union if I know these other 3 probabilities, and that's true. But like any equation, you know, if you know all the variables except for one, you can find the thing that you don't know. So, I mean, if you knew any 3 of these 4 things, you could find the other one using this equation. So that's the law of unions. Now, sometimes 2 events may be what you call mutually exclusive. Mutually means to each other. Exclusive, they exclude each other. So So 2 events are mutually exclusive if it's not that they can't both happen, it's that they happen together with probability 0. So if that probability equals 0, for any two events, that's what you call mutually exclusive. Now, there's a little bit of philosophical distinction to be made here. We already talked about disjoint. We said two events or two sets are disjoint if they have no members in common. So here are two sets. Those are disjoint sets. Their intersection is empty. So if two events are disjoint, then they are also mutually exclusive. Imagine the experiment of rolling a die here. There isn't any outcome that's both odd and even. Okay. So the probability of the intersection, the probability of the empty set is 0. And that was one of our axioms. That always has to be. Mutually exclusive is almost the same, but not quite. Over here, my experiment is rolling a die. And I have a finite set of outcomes that are possible. We consider an experiment where I'm throwing darts at a target. And here I've got these two events. I've got the left target and the right target. I throw the darts. And, well, there is this one point, the way I've drawn the picture, where the two sets touch. So the intersection is not the empty set. It does contain that one point. So the way I've drawn it with the circles touching, L and R are not disjoint. And yet the probability that your dart would hit that point exactly is 0. I'm talking about a mathematical point here. It's tiny. It occupies 0% of the total area of the square target here. So, there's an event with probability 0, but it is still possible. If you think about are events of probability 0, do they ever happen? Well, sure. Here's kind of a silly way to think about it, but if I throw up a ping pong ball in a fan and it's blowing around in the room, I got it blowing around, it's sort of in a cage up against the blackboard. And it comes down somewhere at a point. And then I ask you, what was the probability of hitting exactly that point? So here's my blackboard. Ten feet across. I throw the ball. Well, first let me ask, now what's the probability of the ball falling there in that little strip A? Well, if I do this in such a way that all locations are equally likely to be hit, then A there occupies 1 foot, and the whole blackboard is 10 feet long. So I get 1/10. Well, what's the probability that I hit right at that specific location right there with the arrow? Well, it's less than 1/10, because it's less than the probability I might have fallen anywhere within that 1 foot. But then I could cut that length in half. Say the probability of hitting that one spot is less than 1/20th. Then I could cut that in half, less than 1/40th. See, the probability that where it comes down is in A is 1/10, but the probability that X equals, I don't know, let's do 5.5. The probability of hitting that exact spot, it's less than 1/10, and it's less than 1/20th, and it's less than 1/40th. It's less than any fraction. There's only one number that's less than any fraction, and it's 0. So there you go. So how you throw the ball up, it falls someplace, and then you ask, well, what was the probability that that would have happened? And you get 0 every time. So events of probability 0 happen all the time. Yeah. So when you say probability 0, all you mean is if you were to throw the ping pong ball up, if you were to repeat this experiment many times in the future, as you do it more and more, what percentage of the time are you going to hit that exact spot? And you're predicting that that would happen 0% of the time if you go on forever, because there's so many other places the ball could hit, and it hits them all equally likely according to your model. Okay. So, mutually exclusive is not the same as disjoint, but it's almost the same. So, we've got our general law of unions. Okay, I can't write. Probability of A union B is P of A plus P of B minus P of the intersection in general. But if A and B are mutually exclusive, then that last part is 0. So you could just ignore that part, it's 0, and you get the probability of the union is the sum of the probabilities. Say, didn't we already know that because of our axioms, Kolmogorov's axioms? Well, no, that was for disjoint events. And it was for finite probability models only. Okay. And the demonstration of why this equation is true with the flowers, I was assuming a finite sample space. There were only 20 flowers. But this works in general. You can talk about probability just fine in other situations where you can't count the outcomes, but you can still assign percentages. Okay, so that's all for this lecture, and I'll do a separate recording about conditional probability, the law of intersections, and then another one after that on the law of total probability, and then you'll have a full set. Okay, so that's it for this session.